Thank you very much, Yoshi. Good afternoon, everybody. Thank you for the invitation. I'm grateful that you've asked me. So what we're currently doing is trying to gain an understanding of how faults work, how earthquakes work, by studying continuous geophysical data. Specifically, in this case, we're studying characteristics of seismic data, the full seismic waveform. What we're discovering is that there's rich information contained in the seismic signals emanated from laboratory faults and also faults in Earth in some cases that we were not aware of previously. We're going to talk about the laboratory analyses we've done, then talk about slow slip in Earth and some results and perspectives. Next slide, please, Yoshi. So the question is, how do we capture the controlling physics of such a complex system? You can have a very undulating fault plane with many asperities. You can have interacting faults, etc. And the question is, can new data analyses approaches help? Since we're sort of at a maximum of information we can obtain from classical approaches. Next slide, please. So I think we can move on from this. Next slide. So here's the basic question that I mentioned a moment ago, and that is there information regarding fault slip contained in the background seismic noise, the noise we have previously discarded except for imaging purposes, such as empirical Green's functions, if you're aware of those. I'm going to give you a quick summary of some of the work to date, and I just want to mention that there's a large team of people working with us, both at Los Alamos and elsewhere, and I am the spokesperson, so the actual people doing all of the hands-on work are not speaking today. So what you see on the bottom part of that slide is a classical seismogram. There's a compressional wave arrival, a shear wave arrival, and the surface waves. And the question we're posing is, what's happening before the onset of the P wave arrival, and what's happening after the surface waves have arrived? Is there information contained in the signal that we typically thought was just noise? Next slide. So this is on your left, you see a cartoon of the experimental setup that we were using for the laboratory experiments. This is a biaxial shear device. What the system is, a 3-block system with 2 fault gouge layers between the 3 blocks. As you can see, you apply a horizontal load to hold the system in place, and you drive the center block down at some constant velocity. Initially, and during that time, you're recording such things as the shear stress, the horizontal load, therefore you can calculate the bulk friction. We're also recording acoustic emissions. We're recording the fault gouge thickness and other characteristics as well. So we have a very controlled system here where we can control stick slip or slow slip behaviors in the laboratory. And what you see just above the apparatus on the left are a series of a signal that shows a series of earthquakes in the laboratory. So you're looking at something like 15 signals in that signal you're looking at. So if we look to the center panel, we look at panel A, we see 2 earthquakes. So you note there's a shear stress signal as a function of experimental runtime. You see 2 earthquakes. You see 1 earthquake, then you see a buildup in the shear stress. We get to a critical state and nucleating state, and then the system fails again. We're detecting the acoustic emission signal. That is the signal just below the shear stress signal. And it says strain, but that is dynamic strain. And you can see there's a burst of sound associated with each earthquake, a large amplitude signal. And there's also some sense of precursors on that left-hand earthquake. You can see a precursor, at least one precursor that precedes that. You can see a zoom of that on the bottom right in the C panel. So this is a classical precursor that we see in the laboratory. They're also quite common preceding earthquakes in Earth, but they are not always there, as many of you may be aware. Also on the left, you see that what appears to be just noise. We call this the physics of distant failure. The signal appeared to just be noise coming from the system and nothing else before we started to apply machine learning tools to analyze that signal. Next slide, please. So how do earthquakes evolve? We're going to use a data-driven approach using machine learning. Next slide. So what we're trying to do is, this is a figure that came from a review paper that we wrote a couple of years ago in Science. And the idea is to show how different this approach is. You're letting the data tell you what is coming out of the system, in contrast to doing classical analyses like Fourier analyses, etc. Next slide, please. So this is just a quick review of supervised learning in case you're not familiar with it. We have an input signal in this case. This is seismic or acoustic emission data that is continuous. You derive what is known as a statistical feature space from that. It's a large space of statistics regarding that input signal. You see if you can map that feature space to determine fault properties, one sort of fault property or another. In our case, we're most interested in shear stress and fault friction. We train that model using quite a large number of experimental data. And as we build the model, that is the machine learning algorithm, the f of x. So once the model is built and we've validated the model, then we test it on data the model has never seen before. That's the general approach of supervised learning as we apply it here. Next slide, please. So here is, on the top is again a dynamic strain signal. So this is just the acoustic emission coming out of the 3-block system that you see again at the right. We've derived the feature space and we're trying to map the feature space to inform us about what the instantaneous shear stress on the fault is at present. So on the bottom, you see the shear stress signal. The gray panel, the gray overlay you see is a time window. And from that time window, we're extracting the statistics. And from those statistics, we're trying to predict stress on the fault. So that's the approach. We apply a moving window analysis. So you move a window through the time series signal, and at each moment in time, you pose the question, can I map information from that time series signal, from that acoustic emission signal, to the shear stress? And so that, again, is the procedure we're using. And in the next slide, you can see the results, the initial results we were obtaining from the laboratory a couple of years ago. So on the left-hand panel, you see the acoustic emission data, so it's arbitrary amplitude, and on the bottom axis, the experimental runtime. What you see in the green shaded region is the data used for training the model, and the blue or gray overlay shaded area is testing the model. So for the model training, again, we use the full acoustic emission signal. From the left-hand panel, panel D, we're trying to map to the shear stress signal. So on the right-hand panel, you see shear stress as a function of experimental runtime. So again, once the model is trained and validated, and we use the green shaded area for both training and validation, then we test with the data on the right-hand side of each panel. So that's, again, a review of the total procedure we're using. Next slide, please. So this is showing you on the left-hand side, once again, the acoustic emission signal as a function of experimental runtime, the bottom axis. You can see in that signal bursts of sound, large amplitude signals that each of them are associated with a earthquake in the laboratory or a lab quake. On the right-hand side, you can see the actual measured signal as red dashed line. So that's shear stress as a function of experimental runtime. And you can see that, again, the shear stress signal measured on the apparatus is the red dashed line. I'm repeating that. The blue solid line are the predicted signals that come only from the acoustic emission signal once the model has been derived. And by the way, for those of you familiar with these kinds of approaches, this is a simple approach. We'll call it old style approach using decision trees, in this case, random forest. We use several different kinds of decision tree model approaches. I'm sorry, this is XGBoost, which is a sister model of random forest. But you can see that the predicted values using the moving window, and by the way, on the left-hand side, you can see a single moving window. And you can see that, excuse me, I have some background noise here. You can see that the moving window is the window length is relatively short. It's a matter of a few seconds. There's an overlap in that window that we apply as well. I'm not giving you those details, but they're contained in the papers. And what you see on the right-hand side then is a remarkable representation of the actual data. And so it was a real surprise to us initially when we saw this kind of result, because it told us that at any given time, there was information contained in statistics of the acoustic emission signal that was informing us about the state of the fault in regards to shear stress. If you could develop a model for also for the displacement on the fault or even the gouge thickness, these were separate models, it also worked. So it was, again, we were actually quite astonished that this was working so well. And it told us there was much information that we contained in the acoustic emission signal, the continuous signal, that we were discarding. Next slide, please. So here's why it worked. If you look at the right-hand panel, panel B, you can see the top dynamic, on top you can see the dynamic strain or the acoustic emission signal as a function of experimental runtime. And you can see three of the statistical characteristics of that signal below it: the variance, the kurtosis, and threshold. This is simply an amplitude thresholding procedure. And you can see that in particular, studying the variance, for example, you can see the buildup in the variance of the signal until there's a burst in the acoustic emission signal, and that is associated with the laboratory earthquake. And that repeats itself through several cycles here. You can see 3 full earthquake cycles and a little more. There's also information contained in the kurtosis of the signal, thresholds, and many of the other statistics. But the most important was the variance. But we found that all the energy-related statistics contain information regarding the state of the fault. So there's no magic here. It just turns out that there was information contained in these statistics that we just weren't aware of. We weren't looking at them. It didn't occur to me or us to look at the kurtosis of the variance, for example, of the acoustic emission signal. Had we done that, we would have known that there was information there, but it took the machine learning procedure to tell us this. There's also information contained in the signal regarding the time to failure, which is also quite remarkable. And that's probably logical, right? Because, excuse me, my computer has just signed me off. So there's also information contained regarding the time to failure. And I'm just signing back on. Apologies for that short delay. So on the left-hand panels, you can see the shear stress signal over three slip cycles. And just below that is the time to failure just based on those slip cycles. So it's a countdown to time to failure, a linear countdown. Below that, you can see that same signal as a red dashed line once again. And overlaying on that is the blue signal, which is the predicted time to failure. So quite remarkably, as soon as you have a failure in the system, it points to the time of the next event. and the countdown improves as you approach failure. It's not perfect, but it's pretty good, as you can see. So it turns out we can predict time to failure, and we can also make an estimate of magnitude, which is fairly remarkable as well. The estimate of magnitude is not as good, however. So we can predict time to failure and to some degree magnitude. Earthquake location, we have the location, of course, because it's a single fault plane slipping. Next slide, please. So the question was, what happens if you take this approach to Earth? As many of you know, maybe all of you know, repeat times of earthquakes in Earth can be very long, typically very long, tens to hundreds, sometimes thousands of years. So you don't have sufficient data to run this kind of procedure, since we only have data back to the 80s at best. For example, the HRSN array in Japan, where it has been recording continuous data now for only about 30 to 40 years. So we face this problem worldwide. So what we decided to do was to look at slow slip and tremor in Cascadia. The reason was because we have slow slip cycles that are quite regular, on the order of every 14 months or so. And they've been recorded for about 30 years now with continuous recordings. And we have GPS as well to measure surface displacement, which would be a proxy for what we were doing in the laboratory with either displacement or shear strain. So the next slide, please. So I think everybody in the room is familiar with, excuse me, looking at this kind of plot of subduction zone where you have the locked region and you have slow slip and tremor that is occurring below that down the fault plane. Tremor was discovered by Obara-san back in about 2000, and since then it's been discovered in every subduction zone in the world. So we're looking at the region that's slowly slipping, and in the following analysis. So next slide. So this is a very well-known figure from Rogers and Drager from a paper in Science that was published in 2003. And what you see is the east displacement of the recorded by GPS on the Earth's surface. And on the right-hand axis, the black, you see the tremor activity over 10-day time windows associated with that slip. So you can see the zigzag behavior you see in red with blue dots is showing the behavior of the slowly slipping fault. Each decrease shows you a slow slip where the overlying plate is lurching seaward back toward the ocean. And then there's a coupling. The plate is moving eastward in this case again, and until the next event takes place. So you can see how regular the events are, again, which is why we went to Cascadia to conduct this study. Next slide. So next slide, please. So this is just a map of the region showing Vancouver Island, just on the west coast of Canada. These are both seismic and GPS stations. I won't go into details here. Next slide. We're using a single GPS station and a single seismic station here. And I'm just going directly to the result now. We're using the same general approach. In this case, it was XG boost. What you see on the left-hand axis is the GPS displacement rate. This is a displacement rate rather than direct displacement as a function of calendar time. There's a data gap here between 2012 and 2013. Thus, there's data missing. But previous to that and following that, the red is showing us the GPS signal recorded at all time during this time period from about 2011 through about almost 2018. The blue is the prediction once a model is trained, and so that we're applying it to data that the model has never seen before. And you can see that it does quite a good job in characterizing the sort of average behavior that the GPS is showing us. So again, quite remarkably, the approach that we developed in the laboratory transferred to Earth scale. So that, to us, that was a huge surprise and very gratifying. Next slide, please. And again, there was statistical characteristics. There was a reason for that, because the energy statistics were what the model was identifying that were important, and that the model used to make these kinds of instantaneous predictions. I won't go into the details here. Next slide, please. So we can also predict the time to failure in the exact same way we did in the laboratory. And that's the bottom right-hand panel. The red dashed is the time to failure assumed from the slow slips that are well known in Cascadia and elsewhere. And the blue line is the predicted signal. So the next slide, please. So I'm going to just mention one last thing and then stop. But the question is, how do we address the complex seismogenic faults in Earth with long repeat times? This is the question we are all interested in, right? Everybody listening in and our team, we're all doing all this work because we're interested in trying to see if we can understand ways to obtain more information about a seismogenic fault, which faults that give us the damage from an earthquake. Again, we only have sparse data because typically we only have data measured over a portion of a slip cycle. So next slide, please, just to describe our general approach. We're doing this right now. We've spent probably the last almost 2 years working on this problem, and we're using deep learning in this case. These are more sophisticated models that can tell you much more about what's contained in a system. However, they're somewhat opaque, so they're difficult to understand what they've done, but they function very well. What we're trying to do now, based on a lot of work that we've done, as I mentioned, over the last 1.5 years or 2 years, what we've discovered is that applying our methods directly to seismogenic faults so far hasn't worked. So we're developing approaches where we're training on numerical simulations to predict laboratory behavior with the goal of applying the same approach in Earth. So far, this is working very well. We have a paper on the archive currently that describes the approach where we apply the transfer learning based on training on simulations and then predicting behavior in the laboratory of the shear stress and friction. The model also involves cross-training for those of you familiar with deep learning. But I won't go into the details for lack of time. But so we're using an encoder-decoder deep learning style model. So that's the general approach we're taking, and we don't know where this is going to take us. We don't know if this is going to work. The Earth is really complex, much more complex than the laboratory. So it's hard to know whether this is going to work or not. But we're optimistic based on what we've seen so far that we'll progress on this problem. Next slide. Just a note that we'll have a machine learning and solid earth geoscience conference in March in Santa Fe in New Mexico. We've held this in the past, but because of COVID, it was terminated for a year. Next slide. So the take-home message is the noise is the signal giving us insight into fault physics, and it's the machine learning tools that reveal it to us. Thank you so much for your attention.